Good afternoon, all. So let us continue from what we saw in the last class. If you remember, we started off with the different number systems and how to represent a particular number system. And later on, we will be doing conversion of these number systems from one form to the other form. One such example was given here, right? So this was one example that we gave, how one number system can be represented in equivalent other number systems. Also, we saw that these number systems with bases, right? So 2, 8, 16, 10, these are not the only number systems that are possible. Any number you like can be considered as a base, and then you can create your own number system also. All you need to do is you have to identify different symbols for the number system, and then you must follow the steps that we are going to tell how to convert from one number system to the other number system. First, we started off with a decimal number system, and then we had how we just saw how to represent the integer and the fractional part, and also we saw how to represent or how to add two numbers in decimal number system. And we also said how computer will do subtraction by doing addition, right? So I'll just slightly repeat and then we will proceed on to the next part. So if you look here, as humans, we do the subtraction by like this 100 minus 54, but computers, what they do is they do the subtraction by addition, meaning they will add this number with the negative number. So which means that first we have to represent minus 54 in a negative number, and then we will add that with the 100 with the this 100 here. So that is how we do subtraction by addition. Also, since this is a decimal number system here, there are two complement that are possible. Complement in the sense representing the negative numbers. Okay. So we are going to complement this negative number and then we are going to add with the original number. So that is what it means that we have two complements. As the decimal number system's base is 10, we have two complements here, the 9's complement form and 10's complement form of representing the negative number. We saw an example in the last class. What is 5462 minus 1234? If you directly subtract these two numbers, we know that the answer is 4228. Instead, what we should do is we have to find the complement of this and then we have to add it. As I said, we just saw the 9's complement form. Okay. We just saw the 9's complement form. What is a 9's complement form? Is you subtract this 1, 2, 3, 4 from 9999 and then you add it. So if you look, let us do more 9's complement representations. Yeah. Now, how do you represent this 1, 2, 3, 9's complement of 1, 2, 3, 5 here is? The 9's complement is very simple in the sense all you need to do is subtract this 1, 2, 3, 5 from 9999. So when you subtract 9999, it is straightforward. There is a mistake here. So this should be 4 because 9 minus 5 is 4. And here it is 6. This is right. 9 minus 2 is 7. And 9 minus 1 is 8. So 8764 is the 9's complement of 1, 2, 3, 4. Meaning minus 1, 2, 3, 5 is represented as 8764. Similarly, 8 to 6.27. How do you do that is all you need to do is you subtract 999.99 from 8 to 6.27. So it is straightforward again. 9 minus 7, 2, 7, 6. Sorry, 9 minus 6 is 3, 9 minus 2, 7, and 9 minus 8, 1. Right? So this is how to do 9's complement. Yes. Yes, any doubt, Rahul? Okay. Now, all right. Now, what is a tens complement? As I said in the last class itself, your tens complement is nothing but you take 9's complement and then add 1 to it. In fact, what is 9 plus 1? 9 plus 1 is 10, right? That is how we are doing the same thing. We take 9's complement and then add 1. Okay. So, or why, you might ask me a question, why should we do this? Instead, we can subtract it from, say for example, let me look at the 3, 4, 2, 6, right? We are going to do a simple example of taking tens complement of 3, 4, 2, 6. So instead, you can also do this also. That is, you take 5 digits and then subtract from 3, 4, 2, 6. Okay, so what will be the answer? So the you have to take a carry, right? So 10 minus 6 is 4. You will take a carry here, so it will be 9. So 7. Again, one more carry here. So this is going to be 5. And then one more carry here. So this is going to be 6. So 6, 5, 7, 4. Instead, you take 9's complement and add 1, that will be much simpler. How it is going to be simpler is, what is 9's complement of 3, 4, 2, 6? All we need to do is subtract from 9999. So 3, 4, 2, 6. When you subtract, it is straightforward, right? So it is 3, 7, and then 5 and 6, right? And then you have taken, so this is the 9's complement form. You add 1 to it. When you add 1 to it, it is 4, 7, 5, 6. It is the same answer. So either you can subtract from 10,000 minus 3426, or you take 9's complement and add 1. Always, this particular method is an easier method. Why easier method is, it is easy for you to subtract from 9999 rather than taking zeros and looking for carry forward, trying for carries. So that is why you take, this is a easier method. You take 9's complement and add 1. So that is how it is done here. So two examples here. What is the tens complement of 3426 is 9999. You take 6 by 73. So this will be your 9's complement. This will be your 9's complement here, and add 1 to it. Add 1 to it, you get 6 by 74, and this will be your tens complement number. Okay. So similarly, another example here, 267.805. So the first step is take 9's complement, that is subtract from 999. So the number of digits you have, all you need to do is subtract it from that. Okay, all you need to do is subtract it. So it is straightforward, 491 dot 227, 2 or 3. So 732.194, which is your 9's complement here. And you add 1, what you get is the 10's complement. So this is how you take 9's complement and 10's complement. Please note here, any base you take, say for example, if you are taking a binary number system, its base is 2, and then we have two complements here. One is the 2's complement, and other will be 1's complement. You take by base as 5, you have 4's complement and 5's complement. You take base as 7, you will have two complements, which is one is 6 and other is 7's complement. So all the procedure here are same. What you need to do is, in case, say for example, you are having a base of 5, then you are taking 4's complement, you have to subtract from 4, 4, 4, say 3, 4, 2, 6 is to the base 5. Let me do it on notes here. Okay. So say for example, we have 3, 4, 2, 6. We have to take 5's complement, we have to take 4's complement. Why 4's complement is because this 3, 4, 2, 6 is to the base 5. If that is the case, all you need to do is subtract from, first take 4's complement, which is 4, 4, 4, 4. Number one, the mistake here is you will not have 6 here. Okay, say let us consider 0. Why you will not have 6? Because with a number with base 5, the symbols that are possible are 0, 1, 2, 3 and 4. These are the symbols that are possible. So if you have 6, then it is not at all corresponding to base 5. So the number 3, 4, 2, 0, first let us take the 4's complement here and we subtract. So when you subtract, it will be 4, 2, 0 and 1. So this is your 4's complement. In case you want to take 5's complement, all you need to do is add 1 to it. So 1025 is the 5's complement of this particular number. Is there any doubt? Because all these things in a summarized way, you will not find it in books. Okay. Now let us do subtraction, real subtraction. All we have done in these two examples is we have taken different numbers and we have found out 9's and 10's complement. Now let us do the real subtraction by using 9's complement. Say I want to subtract 745.81 minus 436.62. We have already done example, but okay. So let me do this on notes. So all I'm going to do is 745.81, I believe. Yeah, 745.81 minus 436.62 minus 436.62. Okay. Now first let us subtract and keep the answer so that I can verify it later. So what is this subtraction? This answer is going to be 9. There will be a carry here. So it is 1. So this is going to be 9 and then 0 and then 3. So this is your answer. Please note that the answer will be a positive number. This is a positive number because 745 minus 436. So it is going to be a positive number and the answer is 309.19. Okay. Now, how should I do it? In case of computers, I have to first take the 9's complement. 9's complement of what? What is the 9's complement of 436.62? So I have to subtract from 999.99 minus 436.62. So this is going to be, I can do anyway. So this will be 5 because there will be no carry, right? I can do it faster. 3 point is going to be again 3 and 7. Now what I do, I have to take, okay, so if I'm doing 9's complement, so this is what is the 9's complement. This, all I need to do is I need to add this particular 9's complement with the original number. What is the original number? 745.81. So 745.81 is the original number and the 9's complement number is 536.37. Okay. All right. Now I have to add it. If I add it, what will be the number? It will be 8, 1, remainder 1, it will be dot 12, and then remainder 1, 8, and then it is 12. 128.18. Now we are having only 3 digits here. We are getting a carry here. We are getting a carry here. So what we need to do whenever we are getting a carry here is,
Excuse me, sir.
yes.
Yes. Sir, the ninth complement was 563.37.
Oh, I'm sorry. Thank you. Okay, I'll redo it. I'll redo it. Okay. Yeah, so it is 563.37. I have to add it. So it will be 8, 1, and this is going to be 9, remainder 0, yeah, 10, 0, remainder 1, then 12, and this is going to be 13. Now I'm having a remainder here. Sorry, 1 is an additional term that I'm getting here. So whenever I'm getting a 1 here, when I'm performing this addition, this 1 needs to be added to the last decimal place, last digit place. So 8 plus 1 becomes 9, and this is going to be 1, 9, 0 and 3. Now let us verify it with our actual original answer. 309.19 is our 9's complement way of answer, and our straightforward method also it is 309.19. So this is what is the answer, and this is how you do it. Let us take maybe one more example where this particular answer becomes a negative answer. Instead you do the reverse. What do you mean by reverse? If I subtract 436.62 minus 745.81, then obviously your answer is going to be negative, right? Let us see that particular example in case I have. Okay. We'll come back to the tens complement later now. Yes, I have that example. Now, in case if I subtract 436.62 minus 745.81, my answer is going to be, so this is the actual straightforward subtracted answer, which is minus 309.19. Okay. Now let us see what will happen to the remainders. Now first what we need to do, we need to convert this negative 745.81 into a positive number, which means that we will do the 9's complement form. So 9's complement of 745.81 is 999.99 minus 745.81. So do the subtraction here. So it is 8 here and 1, 4, 5, 9 minus 7 is 2. So 254.18. Now what I need to do? I need to add this with 436.62. So when I add this with 436.62, all I get is 690.80. But what is my answer? My answer here is, actual answer is 309.19. Then where is that we are doing a mistake? Where is that we are doing a mistake is, please note that when we add it, you are not getting a carry also. No carry means it is a negative number. So the answer you are getting is a negative number, and we are doing a 9's complement, which means that this number is nothing but 9's complement of some number. Okay, so if this is a 9's complement of some number, let us take 9's complement once more to get the original number. Okay, so what is the 9's complement of this particular number? So 9's complement of this number is 999.99 minus 690.80 will be 9, 9 minus 8, 1, 9 minus 0, 0, 9 minus 9, 0, 9 minus 6, 3. So it is minus 309.19. Okay, understood? Okay, so maybe I'll repeat it maybe. So, okay, I'll do this particular problem on notes maybe. Yes. So now, let me take a simple number. I'm going to subtract, say 75. Okay, I'm going to subtract 32 minus 75. Okay. So obviously, what is this number? It will be 75 minus 32 is, so this is going to be 3 and 4. So the answer is going to be minus 43, right? The answer is going to be minus 43. Now, I'm going to perform 9's complement subtraction here. So first is, what is 9's complement of 75? So 9's complement of 75 is 4 and 2. So 24 is the 9's complement of 75, and I'm not getting any carry here. If I am not getting any carry, this means that this is a negative number. If this is a negative number, which means that this is a 9's complement of some other number. So taking the 9's complement of this negative number 24, what is the answer? So this will be 5 and oh, I'm sorry. So okay. So I've taken I've skipped a number. Just forget about it. Okay. Now I have taken a 9's complement here. Since I have taken a 9's complement, let me add this with the number. So 32 plus 24 is going to be 6 and 56. Now I'm not having any carry here, and at the same time, if I don't have I am not having any carry, no carry. So which means that this is a negative number. This is a negative number, and which means that this is a 9's complement of some other number. So taking one more nines complement will get me an original number. So 99 minus 56, this is going to be 3 and 43. So and the answer will be negative. So it is minus 43, which is what is the same answer we got. So this is the procedure you need to follow when you are getting negative answers and when you are getting positive answers. Let us do the similar thing for tens complement. The procedure is the same, but only difference is um, whether to look, there will be a difference in the carry part only. So let us see how to do it. First is a larger quantity minus a smaller quantity. So we will take tens complement here. If we take tens complement, it is nines complement plus 1. So first step, so step 1, take nines complement. Okay. Step 2, add 1 to it. So this is your, this is what is the number. Step 3 is add with your original number, add with the original number. So what is the addition, adding with original number 2928.54? We add the tens complement number 9583.27. When we add, we are getting 2511.81. Please note that we are getting a carry here. If we get a carry, it means that it is an indicative of the answer is a positive one. In previous case, if we get a carry, what we used to do is we will add it with the last decimal point here, right? But here we will ignore the carry. So that is the only difference with the tens complement number. You will ignore the carry here. Okay. And whatever the answer that you are getting is your actual final answer. Okay. Now let us take a smaller number subtracted from a larger number, or a larger number subtracted from a smaller number. So obviously you can see straightforward from here that the answer is going to be a negative 1. So if the answer is a negative 1, so it is what we used to do. Let us follow the same process. My first step will be take nines complement. Second step is add 1 to it, and then the answer I will add it with this particular number, with the original number, and I will have to check whether I'm getting a carry or not. Obviously, nines complement of 2928.54 is, it is, we will just subtract here 9 minus 5 4, 9 minus 5 is 4, so 9 minus 4 is 5, 9 minus 5 is 4, 9 minus 8 1, 7 0 1. Okay, since this is a tens complement, I am adding 1 to it. I will get a tens complement. Now with this number I will add it with my original number, which is 416.73. So 416.73 plus 707, I am not getting any carry here. Whereas in the previous case, what? I got a carry. If I get a carry, it means that the answer is positive and I will ignore the carry. Whereas here, if I don't get a carry here, my answer is negative. If my answer is negative, again, it means that this is a tens complement of some number. So I will take one more tens complement of this number. So tens complement, you know, nines complement plus 1. So with this result, I am taking a nines complement and then adding 1 to it. So the result I get is 2511. Based on the carry that I get or I don't get here, I will put this particular sign whether the answer is negative or positive. Okay. So to summarize, no carry indicates that it is a negative number. Okay. And hence nines and tens complement answers, you will have a negative answer. If there is a carry, then it means that in case of nines complement, you add 1 to the sum. In case of tens complement, ignore the carry. So this is a simple rule that you need to follow to perform nines and tens complement subtraction. Now let us relook at, somebody is having doubt, I believe. Let's see. Okay, there is, let me, oh, there is no doubt. Okay. Okay, so I've been repeating this. The number systems, for a number system, base is very important. You can have a base of 10 or 2 or 8 or 16 or of any number, right? And if you have that particular base, the symbols will be from, say for a 10 base, your symbols will be from 0 to 9. For a base 2, 0 to 1. For base 16, you are crossing the symbols that you know in numbers, 0 to 9. Then you are using alphabet. Say for example, I am having base 20. If I'm having base 20, then what will happen is I will have 0 to 9 and then A, B, C, D, E, F, 16 is done. So G, H, so 16, 17, 18, 19 and 20. I will have digits till this G, H, I, J, right? So this will be my new number system, not base 16. I am looking for base 20. Okay. All right. Now you will need to understand what is the most significant bit and least significant bit. Most significant bit is, say if I have a number 24653, right? What is the most significant bit is the leftmost digit on the paper is called as the most significant bit, and the least significant bit is the rightmost number is the least significant bit. And in case of binary, the 4-bit numbers we call them as nibble, 4-bit numbers we call them as nibble, and 8-bit numbers we call them as byte. You must have studied all this above. Now we are slowly moving on to conversions. Now first, let us look at the decimal number. You must, before handling the decimal numbers, we have already seen the weights of the positional weights of the different decimal digits. What do you mean by the positional weights? If you recall, in the last class, we just draw some table here and then we wrote here, right? These are the positional weights. So I did for a number with base 10. Similarly, I did for a base number with base 8. Likewise, for any base, you can have a positional weight. Okay. Now, what we do here is let us take one decimal number. Why I'm saying one decimal number is instead in general, I'm taking a number with base as 10. Normally, you will not look like that this number is a base 10. All you need to look at is it will be just simply written as 146.17 to the base 10, which means that this is a decimal number. Okay. Now, how do we represent in terms of positional weights? In terms of positional weights, you all know that this sixth position corresponds to 10 power 0. This corresponds to 10 power 0. And the next position corresponds to 10 power 1. 3 positional weights is 10 power 2. And one's positional weight is 1 by 10 or 10 power minus 1, 10 power minus 2. Likewise, it will keep on going on. Now, how do you represent in terms of positional weights? Yesterday we did a problem. So it is 3 multiplied by 10 squared, 4 multiplied by 10 power 1, 6 multiplied by 10 power 0, and so on. So this combination, I will have 3 into 10 squared is 100, so 300, plus 4 into 10, which is 40, plus 6 into 1, which is 6, dot 1 into 1 upon 10 power 10 is going to be 0.1, plus 7 into 10 power minus 2 is 0.07. So when I add all these things, I will get this original number 346.17. Similarly, this is for a decimal number system. For a binary number system, if I have this, I have to follow the same rule. Rule doesn't change. So this positional weight is going to be 2 power 0. This one's positional weight is 2 power 1. This one's positional weight is 2 power 2. This one's positional weight is 2 power 3. And this one's positional weight is 2 power 4. Similarly, on the fractional side, this one will be 2 power minus 1. This positional weight will be 2 power minus 2. All I need to do is, if I need to get the original number, in this particular case, the original number is 11010.11 is the original number. So if I need to get, all I need to do is I will have to follow the same rule here. That is, this one, you look parallelly here also. This 1 multiplied by 2 power 4 plus 1 multiplied by 2 power 3 plus 0 multiplied by 2 power 2 plus 1 multiplied by 2 power 1, and then so on. Please note here that this is not represented as a decimal number or any other number, though ones and zeros are a part of decimal number, octal number, and hexadecimal numbers. Since 2 is written here, this corresponds to a binary number. So finding the positional weights here, it is 1 into 2 power 4, etc. Now, if you find what is 2 power 4, 2 into 2, 2 into 2, 2. So 16. 16 into 1 is 16. 2 cube is 8. And then 0 multiplied by anything is 0 here. So 2 and then 1 by 2. What is 1 by 2 here? It is 0.5. 1 by 4 is 0.25. So when you add all these things, what you get is 26.75. What you have done here literally is you have converted a binary number 11010.11 with base 2 to an equivalent decimal number which is 26.75 to base 10. So this is how you do a binary to decimal number conversion, right? So one conversion is done. Totally how many conversions we have to do? At least if we handle these number systems, we have binary to decimal, decimal to binary, binary to octal, octal to binary, binary to hexa, hexa to binary. Likewise, decimal to bioctal, octal to decimal, octal to binary, binary to octal, decimal to hexa, hexa to binary. So all the multiple combinations of conversions are there. Now, let us do the same thing. If how do you convert a hexadecimal number to a decimal number? Again, whenever you are applying the weights and multiplying, the resultant will always be a decimal number. So here also you see what is the weight of A. A's value is equal to 10. Am I right? So this you must remember. A value was 10, B value was 11, and then C value was 12, D value was 13, and E value was 14. So these weights you must remember. So just to hold on for a minute. I will be back in exactly 3 minutes. Okay. Okay. I'm slightly early back. All right. So this is how you convert a hexadecimal to a number, a decimal number. So how do you do that? So A to F and this base is 16. So which means this positional weight is going to be 16 power 0. This positional weight is 16 power 1 and this positional weight is 16 power 2. All I need to do is multiply this A multiplied by 16 squared plus 2 multiplied by 16 power 1 plus F multiplied by 16 power 0. And what is the equivalent value of A? A value was 10. So 10 multiplied by 16 squared plus 2 multiplied by 16 plus 15 multiplied by 16. Right? So 16 power 0. So 16 power 0 was 1. So when I multiplied 256 multiplied by 10, 2560. So the equivalent of A to F is 2607, which is the decimal value. So this is how you convert hexa to decimal. So all you need to do is the binary number, the octal number, hexadecimal number, all these numbers, if you are converting it to a decimal number, then simple rule is multiply these numbers with positional weights. Multiply these numbers with positional weights. Yeah. Okay. Now let us take any other base. If you take a base of 5, then again the rule applies the same. It is this, since this is written as 5 here, its positional weight will be 5 power 0. This positional weight is 5 power 1, 5 power 2 and 5 power 3. 5 power 3 is 15 into 5. Okay. So what is 15 into 5? I think 75. So 75 multiplied by 4 is 150 and then 300, I believe, right? So it is 300. Am I right? Somebody can use calculator here. So, and then here 2 into 5 is 10, 5 into 1 is 5, and then dot this one is 5 power minus 1. So 5 power minus 1 is 1 by 5, which is 0.4. So when you add this, so this is going to be 10, this will be 5, and this I suppose 4 into 5 into 5 into 5. So 25 multiplied by 20. So I get 25 multiplied 500. Yeah, I get 500. 500. Yeah, that seems to be yeah, this is going to be 1, right? So 1 into 1 is 1. So 500 plus 10 plus 1, which is 511 point this 4. This one is 0.4. So 511.4 in terms of decimal. Similarly, you take octal also, you follow the same thing, right? Any doubt? Any doubt in conversion from any base number to decimal number? Okay. All right. Now let us move from decimal to binary number. I mean, this you must have studied in your lower classes. 41 to the base 10. You have to keep on dividing it with the base of the binary number, right? Say if you want to convert 41 to the base 10 to binary, then you divide it by 2. So 41, when you divide it by 2, you will have 20, and the remainder you can write it this way, right? So remainder 1. So here 2 we divided by 10, and the remainder is 0. Again we divided by 5, remainder is 0. Here the remainder will be 1, right? So and then here again you further divide, what you have is you have 1 and the remainder is 0. Or you have to travel this way from bottom to top to write the sequence of numbers. What is the number you got? You got, though I have written here, let me write so that it is 1 here, then 0, 1, 0, 0, 1. From bottom to top, if you look, so this is what is the number. Then you write as base 2, which means that the equivalent of 41 in decimal is 101001 in terms of binary. Okay. Now you have to convert 153 to the decimal number to octal number. Now what is that we have seen here? We have seen all base numbers to conversion to decimal. I wrote here, right? So somewhere, yeah. That is, you want to convert binary, octal, hexa, or any other base number to decimal, you multiply it with positional weights. Or you have a decimal number and you want to convert it into any other number, say for example a binary or octal or hexa, or to the base any other base. Here you did multiplying with the positional weights. Here you divided with the base number. You divide it with the base number of the required conversion. Say for example, you want decimal to hexa. The hexa's base is 16, so you have to divide this decimal number by 16. Okay, so if you want to convert to a base of 5, then you have to divide this decimal number with a base of 5. Okay, so that is how this conversion is. If you want to convert 153 to the base 10 to base 8, which is nothing but an octal number, divide 153 by 8. Okay, so obviously if you are slightly behind in terms of multiplication, there is a shortcut. You can definitely use calculators. In calculator, what you do is you type 153. So in calculator, you type 153, then the divided button, and then the 8 number. Okay. When you press equal to, what you will get is you will get in terms of decimal number, right? You get some answer. You get some answer, but this answer will be in terms of decimal quantity. Say for example, 19 point something, 19.2 or whatever it is. So instead of decimal, what you do is there is one more button which is called as the fractional mode, which you used to look like this ABC mode. Okay, when you press this particular ABC mode, then what happens is you will get in terms of mixed fractions, which means 153 by 8, you will get something like 19 1 by 8. So this 19 is this particular number and 1 is the remainder. So you can write 1. Straightforward. Again, what you do is you 19 divided by 8 and press this ABC button, you will get 2 3 by 8. So 2 is this divided number and then 3 is the remainder. So you can easily calculate. This is in case of 8. In case say you are doing a hexadecimal, obviously finding say I expect you to divide 2 5 3 2 1 4 sorry 4 3 any number, and I ask you to convert to hexadecimal, definitely it will be slightly harder for you, right? So instead you can use calculator. Whatever the answer you are getting here, you write here, and whatever the remainder you are getting, you write the remainder here, and then keep on going, right? So this is a easier method for you. Okay. Now, all right. Now let us handle the fractional part. We have been looking only at the integer part so far because fractional part is slightly different to handle. If I have decimal to any other conversion, I have to multiply the fractional part with the positional weights here. So if you remember the positional weights, what is the positional weights? The for a integer part, say if I'm having 24.2, it is 4 multiplied by in terms of decimals. Okay, in terms of decimals, this is going to be 10 power 0. And what about 2? 2 is nothing but 10 power minus 1, or 2 is multiplied by 1 by 10. So here it is multiplication, here it is division. After the fractional part, it is division. When you used to consider the integer part conversion from decimal to any other number, you multiplied, right? So here also you multiply, you do the reverse actually. So it is 0.6875. When you convert it into binary, then multiply with this positional weight 2. If you are getting a remainder, so what is 0.6875 multiplied by 2? It is 1.3750. You take this integer part alone. Okay, and that is you write separately as 1, and what is the remaining? It is 0.3750. So 0.3750 multiplied by 2 is 0.7500. One more, so the coefficient here is 0, so write 0 here, and it is 0.7500 multiplied by 2, you will get a coefficient 1 here, write this one separately, and then only 0.500 multiplied again by 2, so you will get 1.000. Write this coefficient separately. Now, what is equivalent binary value of 0.6875 is, it is 0. You should not forget this decimal quantity. So it is 0. Write in sequence 1011. So it is 1011 is the equivalent decimal quantity, sorry, binary quantity of this fractional decimal part. Similarly, you want to convert to any other base, 0.513 you need to convert to octal. Then what you should do is 0.113 multiply by 8. Whatever the integer part you are getting, write it as a coefficient. So here 0.513 multiplied by 8 is 4.104. So you multiply, so you take this 4 separately, and then remaining is 0.104. So 0.104 multiplied by 8, it is 0.832. So the coefficient again here is 0. So likewise, you have to keep on continuing, and there is no limit. If this multiplication keeps on going, you can also keep on going, but you have to stop somewhere. So here we have stopped here itself. We have stopped here. So what is the equivalent of 0.513 in terms of decimal is 0.40. So this one, 40651 and etc. to the base 8. Okay, you know that after the decimal point, it keeps on going, right? So that is the reason. So now one more example. So we have seen one conversion from fractional decimal to binary. fractional decimal to octal. One more, both combined, integer and fractional part combined. How do you convert it into binary? So 41 you can convert by the normal method, that is by divisional method. The remaining decimal part 0.6875 you can convert it using this multiplication method. So multiplied by 2 you find out the coefficients 1011. All you need to do is you have to combine these two answers and then write it in terms of binary. So 41.6875 is equivalent to the integer part separately, which is 101001 dot the fractional part separately 1011 to the base 2. So this is how you convert a binary number, sorry, decimal number to a binary number with integer and fractional parts. Any doubt? Okay. Now handling the octal part. It is fairly simple to convert from octal to decimal, decimal to octal to binary or binary to octal. So you know that why we are so much interested in octal, why we are so much interested in hexadecimal is because these are multiplicative products of to the power of 2. You know that 2 power 3 is 8. Hence we are interested in octal. 2 power 8 is, sorry, 2 power 4 is 16. Hence we are interested in hexadecimal. Then immediately ask why are we not interested in 2 power 2, which is nothing but 4, right? So it will not give you any meaning, right? The people tried to develop the 4-bit system, but you are having only 4 bits, right? So 0 1 2 3 4, 0 1 2 and 3, this is a half cooked, half baked number system. Hence 4 is not considered. Okay, now how do you convert from binary to octal? All you need to do is, if you are having a binary number, say I'm just writing some random number 11011011112, sorry, 100. All you need to do is separate them into 3, because 2 power 3 is 8, which means that the the 3 power it corresponds to 3 binary digits only. So each octal digit here corresponds to 3 binary digit. All we are going to do is we are going to separate them into 3 binary bits. Always start from the right. So here this 3 can be combined. So here this 3 digits can be combined. This 3 digits can be combined, and this 3 digits can be combined. Okay, now it is straightforward to write the equivalent binary decimal value. We are trying to convert from binary to octal value. So what is 100 corresponds to? 100 corresponds to 4. 111 corresponds to 7. 110 corresponds to 6 and 6. So this is the equivalent octal number. So conversion from B to O, binary to octal, is fairly simple. So the rule is make group of 3 bits from LSB to MSB. So this is most important part. Sorry, this is the most important part. If you are operating for an integer value, if you are operating for integer part, then you have to look from LSB to MSB. If it is for a fractional part, look from after the decimal point. Okay, make group of 3 bits from the binary point for fractional part. Let us take a simple example now. Yeah. Okay, in case, say for example, I'm having some random number. Let me write wherever I'm finding some space. If I'm having, say 1101, right? I have to convert this binary number to octal number. Okay, now what I do? You all know that I need to group into 3. I'm grouping into 3 numbers. What about now I don't have a group of 3, but I have only one number. In that particular case, what I should do is I must always append the required number of zeros to this particular number. Okay, so this can be grouped into 3. So what will be the converted value? 001 is 1, 101 is 5. So this is the converted octal value. If it is after binary digits, after a decimal point, say 1101.1011. If this is the value, then what you need to do is again do the grouping here. Do the grouping from MSB, LSB to MSB in case of the integer value. So here this can be grouped here. Since I'm having only one, I can add two zeros here. But after the decimal point, I will group from the decimal binary bit. So this three can be grouped here. And then since I'm not having any more digits, I will append zeros here. So the equivalent value will be, so 101 is 5, 001 is 1, dot, 101 is 5, 100 is 4. So this will be the equivalent octal value. Okay. So if the last group does not have enough digits to make it to a group of 3, then pad zeros. You have to add zeros to it. Okay. All right. Now, I think we are already time. So how, and immediately you might ask, how did I write this 1, 5 and all those things? The decimal, the binary equivalent of these octal numbers, you must know that binary equivalent of octal is 0000. 1 is 001, 2 is 010, 011, 10. So this you must remember. And how did I get this? How did I get this is very simple here. If I take 7, this positional bit is 2 power 0. This positional bit is 2 power 1. This positional bit is 2 power 2, right? What is 2 power 0? This is going to be, I'll write here 1 plus 2 power 1 is 2 and 2 power 2 is 4. Now add these three things. 4 plus 2 plus 1 is nothing but 7, which is nothing but the 7. If I have here this positional bit is, so in short, I can always write that the positional bits can be 1, 2, 4, and then 8, 16, right? So these are the positional bits here. So this is a second and third positional bits which corresponds to 4 and 2. So 4 plus 2 is 6. So it is 6. Similarly, I have 1 and 1 here, which corresponds to this 4 and 1 here. 4 plus 1 is 5, right? So this is how you need to remember the octal equivalent binary values like this. Similarly, you need to remember the hexadecimal binary equivalents also. Now, yeah, very slightly a longer example here. All you need to do is group them into 3. So what are the groups that I can make? I can make this 3, this 3. Likewise, I have to keep on making groups. I have only 2 bits here, so I will add 0 here. Similarly, towards the, after the binary bits, this 3, this 1, this 3, and then I have only 1 bit here, I will append 2 zeros here. So this one is, I have padded 0 here, I have padded 2 zeros here also. What is equivalent of 0, 1, 0 from this particular table? Yeah, 1 minute. Hello. Yeah. So so we have I have padded zeros here. What is equivalent to 0, 1, 0? It is 2, 1, 1, 0, 6. Likewise, I will convert from binary digits to octal digits. Any doubt? Okay. So we will continue this conversion in the next class also. If there are no doubts, you may exit.